Okay, so here we're dealing with problem 3.7, which requires us to solve for the moment of inertia again for this given figure, except this time we're dealing with two axes, which is our x, which is our horizontal axis, and our z as our vertical axis. Alright, so same first step. Our first step is to, of course, find our parts. Okay, so how are we going to do this? So if you notice here, we are dealing with a curve feature for this figure. Now how we're going to divide this? Okay, we can clearly see that we can divide this into one horizontal rectangle as well as a vertical rectangle as well. So now what about this part? How are we going to separate these parts? Now if we zoom into this particular area, since we know that our second step, we will be gathering the area, the total area of this entire figure, correct? So what we could do to gain the area of this shaded area is to simply construct another shape, which in this case is a square. Now why? Now we are given, remember, we are given the radius, which is 1/8 inches. So accordingly, if the radius is 1/8 inches, we can determine these lengths, which is the same, 1/8 inches. So once we find the area of the square, we can subtract the area of a quarter circle in order to get our area for this shaded region. So coming back here, let's now identify each one of our parts. Alright, so here are our each individual shape. So if you can see, we have encountered 6 of them. And then now let's identify whether we have all its lengths. So over here, we already know that this is 0.064, as given here. Now how about the length? The length is simply, we are given the height, the total figure, which is 1 1/4. We simply subtract 0.064 to get our length. Now for our squares. It's simply the same length as our radius, the radius given here. So we have all our lengths. Now for our last shape, we're given its length, which is 1 1/2, and we're given its width, which is 0.064. So now that we've completed that, let's proceed to the second step, which is our area. So now we simply figure out the area for each one of these shapes. So for here we have a rectangle, which is immediately length multiplied by width. Over here we have a square, which is just side multiplied by side. And for the area of a quarter circle, now we know that the area of a circle is pi r squared. Now since this is a quarter of a circle, we simply divide it by 4. For our last shape, it's just length multiplied by width. So let's do that. Alright, so now we calculated all of our individual areas for each shape. Now you may be asking, why are these negative? Well, if you remember from how we got these shapes in the first place, even though we calculated the area for our squares and our quarter circle, what we really need in the total area of our figure is just this shaded region. So how do we achieve that? That's simply the area of our squares minus the area of our quarter circle, which is why we subtract them here. And then of course, to conclude our second step, we must find the summation. Now for our third step, we need to find the z position, where our centroids for each individual shape. So we're finding its z position upon this axis since we're basing it around the horizontal axis first. So now back over here, let's mark our centroids. So for our first shape, we can assume that there are diagonal lines going from end to end. It is wherever those diagonal lines will intersect. So here we can say it's approximately over here. Now for our second rectangle, we can approximately say it's over here. Now, for our second, third, fourth, and fifth shape, let's head over to our zoomed in figure. Okay, so over here, let's take a look at this figure. Anyhow, they are just mirror images of one another. So whatever is done here will be reflected on the other figure because they're exactly the same. So here, let's look at the square. Basically, its center, that is where it will be. The centroid of our square. Now what about for our quarter circle? It will follow a formula that is very specific to it. It starts from the center and it will work its way through its radius. We can just assume that its centroid will be somewhere over here. So for this shape, we already know our total height for the entire figure and its length. We calculated its length by subtracting 114 minus 0.064. So if we subtract both of those, we get, so this is the length of this entire first shape. Now in order to get its centroid, we simply divide it by 2. Now, since we're basing it upon the x-axis, which is our horizontal axis, we must include our 0.064. That is the position of our first centroid. Now let's figure out what it is for our 6th shape before we head on to our complex shape. Now for our 6th shape, it's basically, as you can see, similar to our problem 3.6. We already know that the total height of this rectangle is simply 0.064. So to get the center, we simply divide it by 2. Now let's head on to our shape number 2 to 5. So for our squares, we already know that this is the centroid, alright? And we already know how long its sides are, which is just 1/8 inches. Now if we simply divide it by 2, we can get to its center, which is this. And we already know that this length is 0.064. So it's basically 1/8 divided by 2 plus 0.064. And then since they are just similar to one another, they will have the same z position. So now let's head over to our quarter circles. So if you remember from earlier, there is a specific formula in order to find out the centroid of a quarter circle. Now what is it? 4r, which is a radius, 1/8, divided by 3 pi. Now let's fill in the values to find out what value this is. Now exactly what is this we're calculating? Well, this starts from our center, the center of the circle. It starts from this center and it works its way out. You got it? Can you imagine it? So whichever value this is, it will work its way out to this. Now, since we're calculating for its z position, which is this, we already know what this value is. Remember, we're basing it upon the x-axis, so we're going up to figure out what position this lies in. So if we got this position already, and we already know what our length is, which is simply 1/8, and we know what this position is, we can figure out where exactly this lies. So simply 0.064, the entire length, 1/8, minus our calculated value. So let's write that down to make it easier to understand. Okay, let's plug these values in. Alright, so we completed our positions. Now let's head on to our 4th step. So for our 4th step, we simply multiply our respective areas for each shape into their z position. Now, of course, let's figure out its summation, which is 0.0537 inches cubed. So, having the summation of our AZ and the summation of our total area, we can finally calculate the centroid of our entire figure. And let's just plug in our given values. Okay, so now, as you can see, our inches square here will cancel out, and our cube. So we're only left with inches, which is what we want because this is our centroid position. So here is our z position. So now for our 5th step, we simply square our z positions. So let's do that. And there you go. So now, let's proceed to our 6th step. We simply multiply our corresponding areas per shape with its new z square. Here we go. So now, let's take our summation. So with this, let us proceed to our final step. Okay, so for our final step, we're gonna calculate the moment of inertia for each individual figure. We found out their centroids. So now our task is to use formulas. Each shape has their own corresponding formula for their own moment of inertia. So let's see what they are. And here you go. If you recall from problem 3.6, we only dealt with this formula, because the shapes that we're provided with were only rectangular shapes, and hence this is used for rectangles. Now what about for this? We're dealing with squares where all sides are the same. So it's basically this formula, except since all the sides are the same, there's no use grouping them into base and height, since they all have similar lengths. Hence we use a to the power 4, which is all of its sides. Now since we're dealing with the quarter circle, this is its formula for calculating its moment of inertia, and we simply plug in our radius to figure that out. And then always remember, by the way, that our base is always the side that is parallel to our axis. So later on, we'll be changing our axis and we'll see what changes can be done to this formula to suit that. And then, as you can see, like since we calculated for shape number 2, shape number 3, and 5 are similar to their previous shapes. So hence, they would have the same value. But regardless, you can see which formulas fit in with which shape, and used accordingly to get our values for their moment of inertia. Now, as always, we're gonna sum this all up to get our total, which is 0.0089 inches to the power 4. So now here we're gonna utilize our parallel axis theorem. This is upon our x-axis, our horizontal x-axis. So we already have the values that we need, and hence the answer that we get is 0.0418 inches to the power 4. Okay, so with this answer, we can already calculate our moment of inertia for our entire figure based on the centroidal x-axis. So here is our moment of inertia formula for our entire figure. Now, even though, if you recall in our problem 3.6, even though this shared the same notation, here we are referring to our entire figure, while this is referring to the individual shapes. So since the question is asking for the moment of inertia for entire figure, this is the formula that we are going to ultimately utilize. And hence, since we already have our values calculated, we simply plug them in. Our moment of inertia for our figure upon the centroidal x-axis is 0.0257 inches to the power 4. And that is our final answer.